Welcome to the course Introduction to Electrical Engineering. We have a lecture 29 on transformer part 1. Starting from introduction about outline of presentation of today, we will discuss working and construction of transformer, then classification of transformers, losses in transformers, ideal and practical transformers, phasor diagram of transformer on no load, and we will have a solved and unsolved exercises followed by references. So, starting with the introduction, we already discussed that what is the need of the transformers. This is the backbone of AC system, and it is transformer is responsible why we won the this AC and DC war, and it has gone in favor of the transformer in spite of many deficiencies. So, you can call it this transformer allow us the generation of electricity at optimum voltage, transmission of electricity at optimum voltage, and then distribution of electricity at optimum voltage and utilization of electricity at optimum voltage. I mean, you can just an example here, without a transformer the efficiency of power transmission and distribution is very low. Let us say we have a typically a power plant and we have a 200 kilometer transmission line length, and here we have a let us say 12 volt DC connection and we have a 120 watt light bulb. So, assuming the resistance of line typically a 0.0001 ohm per meter, it will become 20 ohm for 200 kilometer line, and the current required for to glow the bulb I equal to P upon V, that is typically 120 watt divided by 12 volt, that is 10 ampere, and total power loss in the line will be I square R, that is 10 to power 2 into 20, that becomes 2 kilowatt, 2000 watt 2 kilowatt. So, virtually you can call it like a for 120 watt we will be dissipating the power of 2000 watt. The efficiency of this will become P output divided by P loss plus P output, and that is 120 divided by 2000 plus 120, that is 100, that is it means efficiency is 5.66. So, it means your 94% losses are going to be into the transmission system. So, to improve this efficiency, decrease the current in the transmission by increasing the voltage for same power, and by power transmission at high voltage, while utilization at low voltage is achieved by using a transformer, and this allows generating plant to be located economically at distance from electrical consumers, and this transformer which we call it like a receive AC electrical power at one voltage level and delivers the or transfer it to another voltage level, higher for step up and lower for step down, and it needed for in modern power system. The long distance power line can be have a significant I square losses, and same power can be delivered by high voltage transmission line at a fraction of current and with much higher efficiency, and this feature is one of the main advantage of AC transmission and distribution over DC system. So, step up transformer and at generator and step down transformer at consumer, and you can just see here. So, we have a here the color blue you can say at for the transmission, and green color for distribution, and black color here of generation. So, normally we already discussed the generation is normally between your 11 to maximum voltage is typically not more than 13 kV, 11 to 13 kV. With the help of this generator step up transformer, we increase the voltage start to going even in up to 765 kilovolt or 500 kilovolt, 345 kilovolt, 230 kilovolt or 138 kilovolt. That is you can call it like a transmission corridor work at that high voltage, and you can see for a given power what will the current. So, current will be very low, and then we have this substation step down transformer very close to the consumer. So, we have here like a sub transmission consumers or customer at 26 kV or 69 kV, and primary customer at 13 kV or 400 kV, and secondary customer typically at typically you can call it 120 or 240 volt, and power generation, transmission and distribution optimum voltage, and which I mentioned that we generate at optimum voltage, we transmit at optimum voltage, and we distribute at optimum voltage, as well as we utilize at optimum voltage. The transformer allow us, of course, you can see many transformer here. You have a transformer at generating station, you have a transformer, many transformer at distribution level, and that is really why we really need the transformer. So, this is a typical photograph of the power generation transformer, or we call it the power transformer, which are very closely located to the your generator, either it is typically a wind generation or your cold generation or your thermal nuclear generation or hydro generation. So, we have all these transformer nearby of your power generation. and of course, the design requirement is also quite different. Like here the level short circuit level current level is very important, efficiency is also important also. And the transformer in power transmission, you can just see the transmission transformer or transformer for power distribution, you can see on the pole itself. They reduce to low voltage, so that you can transmit it to typically for distributing the consumers. You can see distribution transformer of different size and different level. And then you have a transformer in power utilization like a welding transformer, high frequency transformer used in electronics power supplies. There of course, the transformer in high frequency power supplies, high frequency transformer used in power supply, the very purpose including a welding now, the very purpose is to reduce the size of the transformer. So, as you increase the frequency of the transformer for same induced voltage, you can reduce typically the number of turns, that will reduce your winding material or copper. Apart from that, then you will be, if less number of turns are used, then certainly you will require the core also of a smaller size. For that, so the overall size will reduce. So, you can call it your conducting material is also reduced, your ferromagnetic material is reduced. So, losses are proportional to volume of the transformer, because it is proportional to the weight, and weight is proportional to volume, because density is fixed of your winding material as well as for the ferromagnetic material. The efficiency is improved. So, that is the reason in many applications now we use the very high frequency transformer, even we are going to like a welding transformer around typically 100 kilowatts order of that, and high in switch mode power converters for power supplies for your computers, we are going around 66 kilowatts order of that, because size of the transformer reduced. So, one purpose is that especially in these power supply to provide the isolation, another purpose is to get multiple output, and the third purpose is of course to have a reduction of the size of this transformer. So, many purposes are typically there of using the high frequency transformer in many applications, and these applications day by day are increasing, including like LED lighting or typically your permanent brushless DC motor fan. They are more efficient than your normal other appliances, especially in home appliance industry. It has given a great revolution, this transformer as a switch mode power converter, with the switch mode power converter part of that. Now, coming to working principle and construction of the transformer, and you can just see typically how the history of the transformer have gone. So, in 1882, the Lucien Gallard and John Dixon Gibbs first built up a step down transformer, which they designed with the open iron core, and the invention was not very efficient to produce, and it had linear shape which did not work efficiently. In 1884 in Hungary, Otto Blethy and Miksa Derry and Karoly Jembrowski suggested the use of closed core, and their design was a toroidal shape, which was made it expensive to make, and wire could not be easily wrapped around it. That is typically you can see how the transformer was there. And 1886, the earliest known transformers used for first long distance AC electric lighting system in Great Barrington, Massachusetts, US, and used to transmit power from 25 horsepower steam engine driven alternator generating 500 volt at 12 ampere to power the light bulb at 4000 feet. As you can see the photograph of that transformer. So, now you can call it like how it is considered as a magnetic coupled circuit. The transformer action is based on magnetic coupling, and two current carrying coils with or without electrical contact being them affect each other through the mutual magnetic field, and voltage induced in coil 1 with coil 2 open can be written as V 1 equal to approximately equal to N 1 d phi 1 upon dt, that is N 1 d phi 1 dt into d I upon d I 1. So, that we can say N 1 d I 1 upon d I d phi 1 d I 1 and d I upon d I 1 dt, that is L 1 d I 1 upon dt, that is you call it like a V 1, the voltage if we neglect the resistance of the primary coil. And now, the induced voltage in the coil 2, that is secondary, will be V 2 equal to N 2 d phi 1 upon dt, that is N 2 d phi 1 upon dt into d I 1 upon d I, and that is d I N 2 d phi 1 to d I 1, and that is d I 1 upon dt equal to M d I 1 upon dt. So, this phenomena of current carrying coil inductor inducing a voltage across the neighboring coil inductor is mutual inductance, and the polarity of the voltage induced depends on the orientation or winding of the two coils represented by using the dot convention. typically here you can see the dot here, how it is really mentioned on this, typically on the core we put it, the coil. So, dot convention, if current enters or leave the dotted terminal of the one coil, polarity of the induced voltage, the second coil positive typically or negative at the dotted terminal. So, this if it is going and if it is also let us say coming in, that you can see the dotted here, like which is concept of juxtaposition of that of the two coil. So, this dot convention here we mention if current enters or leave and dotted terminal one coil, polarity that induced voltage in the second coil, the positive negative at this bottom. So, here you have a typically concept in the same way with the dot convention, and these are the typically we can call it possible configuration with the current direction and polarity of the induced and mutual voltages between the different orientation of. So, this is one, this is second convention, that can be typically third convention and the fourth convention like. So, the time domain and equivalent frequency domain description here. So, you have a like a on the primary side you have a applied voltage, C voltage, you have a resistance and inductance, current flowing I 1, and with the dot in the secondary you have a L 2 R 2 and R L is the load resistance, that is second current typically, and you have a typically the convention we can call it the equivalent to here, like you have a Z 1 and you have a omega j omega L 1 and second you have j omega L 2, then the Z L. Now, we can say V t will be I 1 R 1 plus V 1 t, that is your typically you can call it here induced voltage. So, I 1 t R 1 plus L d I upon d t into M minus d I 2 upon d t, and that becomes equal to I 1 R 1 L d I 1 d t and minus M d I 2 upon d t. So, this from this we can get V 2 equal to I 2 R 2 plus R L, that is virtually the voltage across the load, and we can say that is L 2 minus d I 2 upon d t plus M d I 1 upon d t equal to I 2 R 2 L plus R L and minus L 2 d I 2 upon d t plus M d I 1 upon d t equal to I 2 R 2 plus R L like. So, from here we can just put it in bold denotes in RMS value. So, V equal to I 1 Z 1 plus V 1, and that is I 1 Z 1 plus j omega L 1 I 1 plus j omega M minus I 2, and that becomes equal to I 1 Z 1 plus j omega L 1 I 1 minus j omega M I 2, and that is V 2 equal to, we take it I 2 Z L, then we can say here j omega L 2 minus I 2 plus j omega M I 1 equal to I 2 Z L or minus j omega L 2 I 2 plus j omega M I 1 equal to I 2 Z L. So, here from which we can say a transformer is a device which transfers electrical power from one circuit to another circuit, and it does so without any change in of frequency. It accomplishes this by electromagnetic induction, and it works on mutual inductive concept. So, how is the transformer construction? A steel core, you can call it C, consists of laminated steel about 0.35 to 0.7 millimeter thickness, insulated from one to another, and the purpose of laminating the core is to reduce the eddy current loss, which we discuss in the your magnetic circuit, and the vertical portion of the core are referred as a limbs, and the top and bottom portion is the yoke. So, this is yoke, these are the limbs we can call it, and coil P and S are wound on the limbs. So, coil P is connected to the supply and therefore term as a primary, and coil S is connected to the load and term as a secondary, and that is what we call it a transformer symbolic representation like. So, the working principle as you can see here of this transformer, when AC voltage is applied to the primary winding with the secondary open at no load, current flows through the primary, which sets up magnetic flux in the core as you can see here, and this flux links both the primary and secondary coil, induces EMF by mutual in secondary and self in the primary by induction, and the secondary is loaded, then the current flows through the secondary, and this is reflected back into primary winding as induced EMF through mutual induction. And now, we can say in case of ideal transformer, same flux link when both the windings in both the windings. So, we can call it induced EMF in the winding with E 1 equal to N 1 d phi 1 upon dt, and that E 2 equal to N 2 d phi upon dt, and we can say transformation ratio will be E 2 upon N, E 1 will be N 2 upon N 1 equal to N, and the lossless operation will be E 1 V 1 and E2 equal to V2, and that will be V1 I1 equal to V2 I2, and this will be V2 upon V1 equal to I1 upon I2 equal to N2 upon N1, that is small n. So, you can call it EMF equation. AC voltage across primary will be equal to AC voltage generated, that is phi. If we say phi is equal to phi m sin omega t, so induced EMF in primary will be E1, that is N1 d phi upon dt, that is N1 pi m omega cos omega t, and that is 2 pi f N1 phi m into sin omega t plus pi by 2, and the E2 is N2 upon N1 E1, and induced EMF are 90 degree phase shifted from flux. So, RMS value can be computed. E1 RMS will be 4.44 f N1 upon phi m, and E2 RMS will be 4.44 f N2 phi m. So, now coming to classification of the transformer. So, we have a classification based on the number of phases. So, it can be single phase transformer like low power rating, and secondary output AC voltage often converted to DC for use of many electronics appliances, and we have a 3 phase transformer, that is high power rating, can be built in 3 single phase transformer units or can be a single 3 phase unit and used in power system for electrical grid. And this is typically single phase transformer where you have a typically primary winding and secondary winding, and the how physically look like this transformer and how it is in large rating, how this transformer look like with the you have a complete chamber. The you can call it air cooled, that is normally your oil cooled with the fins for to increase the cross section area of the your effective cross section area for the purpose of cooling with the fins. So, oil flow through the fins also. And now, if it is going to be 3 phase transformer, you have a 3 limbs. So, you have a primary and secondary on the same limb of the first phase, second phase and third phase. This we call it the typically core type of transformer, and how it look like this 3 phase transformer. You have a like a typically 6 winding, 3 primary and 3 secondary winding on this transformer. Of course, they can be connected in 2 connection, which we already discussed earlier, can be connected either in star or delta configuration or many other connections like otherwise, and how it look like with the oil cooled and as well as how it look like your air cooled transformer. So, it can be even based on transformation level. So, that is another classification we call it step up transformer. So, secondary output voltage is stepped up and magnified by a specific ratio compared to primary, that is input voltage by using a greater number of turns in secondary winding, and a step down transformer, that is secondary output voltage is step down attenuated by a specified ratio compared to primary input voltage by using a greater number of turns in the primary winding, and this is what you can say is step up, less number of turns in primary and more number of turns secondary. We apply small voltage, you get a higher voltage sine wave only from primary to secondary. And if you have a step down transformer, you have a less turn in primary, higher number of turns in primary, less number of turns secondary. So, you have higher voltage in primary and lower voltage in the secondary like. And this is typical example of usage of a step up and step transformer in power system. So, we have a generating station which generates like I told you 11 kV to 13 kV. We have a step up transformer to increase the voltage order of, we already discussed that it can be like a starting from 120 to like a 1000 kV, and typical example here is 400 kV, which we are using even in India. Then we have a step down transformer to primary step down primary distribution with the step down transformer from 400 kV to 13 kV, and from 13 kV we have now even a step down either 450 in 3 phase or single phase of 240 volt for providing the household supply for many applications like. So, that is you can see you have a 3 transformer in the path of from generation to utilization. Now, based on the construction, we have a core type of transformer. These coils are wound around the 2 limbs of a rectangular magnetic core, and each limb carrying 1/2 of the primary winding and 1/2 of the secondary winding. So, as to reduce the leakage reactance to the minimum possible, and the LV winding is wound on the inside near to the core, while the high voltage winding is wound over the LV winding away from the core in order to reduce the amount of the insulation material required. And you can just see how it look like. You have a your low voltage winding with the green color closer to core, this is laminated core, and high voltage winding on primary on the outer of this, and 2 half winding are put on one limb to another link. So, that have a proper linking. This we call it core type of transformer, and how physically you can see the transformer, that here you have a thicker conductor for the typically for the high typically one winding, and you can have a less thick of another winding. So, how it is looking like a both the limbs you have a primary and secondary likewise. So, based on such construction, another is a cell type of transformer. The coils are wound on the central limb of the 3 limb core, and the entire flux passes through the central limb and divides into 2 parts going to side limb. Consequently, the cross sectional area, hence the width of the central limb is twice of that of each of side limb, and sandwich type winding is used in such a construction. So, you can see here the primary winding and both secondary winding both are on central limb of this cell type of transformer, and here how it look like physically wound transformer on the central limb. You have a primary as well as secondary of this transformer, and here you can compare the core type and cell type. So, here you can have a typically primary of low voltage core near to the core, high voltage that is away from the core, and how the flux is moving in your entire core to in the path. So, you have a primary secondary on each limb in core type. In center in your cell type you have both winding, primary of low voltage you are on inner portion and outer portion high voltage secondary winding on this, only central core is there, but the flux path is of the both side half the flux here center limb take a full flux, and here entire flux flows to entire core like. So, based on the core medium used, so you have a air core transformer, coil wound with around hollow plastic or ceramic material, numerical less flux linkage between the coil, and use high frequency application, radio or television receiver. Of course, you do not want to have a non-linearity into that. So, another is iron or steel core transformer that give a high permeability mu are equal to around more than 1500, and mostly used in transformer in power system, electrical grid, susceptible to hysteresis loss and eddy current losses, because here in air core you do not have a core, so you do not have a core losses, and of course, you have a ferrite core and other type of alloy LIGO used in high frequency transformer, as they offer reduced losses in the core losses, and typically you can see how steel iron core looks like and how your primary and secondary or air core transformer look like. So, this is your, you can call it iron steel core transformer, this is air core transformer, and these are ferrite core transformer. So, how physically they look like 3 different kind of transformer. Now, based another classification based on usage in power system. So, power transformer, large rating transformer used in electrical power transmission network for step up or step down application like 400 kV, 200 kV, 110 kV, 66 kV, 33 kV, generally designed at operated at full load, and distribution transformer, comparatively small rating transformer used for power distribution network starting from 11 kV, 6.6 kV, 3.3 kV, 400 volt, 230 volt, rarely operated at full load, and these are typically photographs of your power transformer. This is the photograph of your distribution transformer of different kind, even pole mounted of maybe of like a 3-phase, single phase, and ground mounted with the oil cooled like. So, now based on application, the classification, the measurement transformer is used for as a current transformer, which is used to transfer the current, is used in measuring the current in a circuit. The primary winding connected in series with the monitor current, and voltage transformer, which is used for measuring the voltage in a circuit. So, primary winding connected in parallel with the monitored circuit, and this is what you can see the current transformer how look like, and it is like a typically the circuit of your current transformer. So, you have a only one conductor of primary, and secondary you have a number of turns on the secondary, which give you the typically the passing only single turn of the power circuit, so that it does not make any drop in the you can call it in the primary, which is like a main power circuit. Then this is your potential voltage transformer or potential transformer, PT we call it. This is normally high voltage, which is used for measuring the voltage, high voltage, and which really we get on secondary very low voltage, so that your normal meter can be used. So, this is like a you can have a circuit and you have potential, and you make a small voltmeter, you can measure the very high voltage with the calibration. As you can see this typically the CT, which give you like a very large kilo ampere, you can bring into only of course into very small ampere of 0 to 5 ampere or so. Here you can have a low volt 0 to 120 volt with the high voltage like also. Now, another is the classification based on your voltage connected in parallel and CT connected in series, that is the application how current transformer connected here, voltage transformer connected here for purpose of measuring the power even from high voltage circuit in case of that. So, based on application, typically another application is like for the purpose of isolation, secondary voltage is equal to the primary voltage, number of turns in both winding are equal. We are providing just an purpose of isolation and used to provide electrical isolation and protection against the electrical shock, that is bathroom saver socket, portable electric tools, also used in suppress electrical noise in sensitive devices like mobile wireless communication. And you can just see how the isolation transformer between two separate winding with the earthing is also provided here, though, so that you have a appliances running with typically with the proper earth and typically earth free, and you do not get electrical shock like So, this is the photograph of isolation transformer. So, these are some applications. Now, coming discussing the losses in the transformer. We already discussed about some of the losses, that we have a hair loss, we have a iron oblique core loss, which are two types like hysteresis and eddy current losses. Then we have a copper losses, this is also called winding losses, and of course, it depends, like if it is a winding is made of the copper, we call it core loss. In general, we call winding loss, but it can be like a winding may be of aluminum. So, that is the reason we call it winding losses. Then you have another lot called stray loss, and we have a dielectric loss. So, coming to description of different losses, the core losses, it includes the both hysteresis loss and eddy current losses, and the first is the typically hysteresis loss is caused by the magnetization and demagnetization of the core as current flows through the forward and reverse direction, and the input flux switches direction. Some amount of the magnetic flux is needed to cause the magnetization in the transformer core to the switch direction, and molecular structure magnetic domains of the core material reverses as the magnetic flux alternates. And this core loss, this hysteresis loss is another common. This results in a heating of the core and power loss proportional to the area of hysteresis loop, and hysteresis loss is mathematically defined. We already discussed pH equal to kh f into bm to power x, where kh is the coefficient of the hysteresis of the ferromagnetic material, f is the frequency of in hertz, and pm is the magnetic flux density in the Weber per meter square. So, this core loss, I mean typically especially the hysteresis loss, it is shown here as a loop. I mean the field direction are randomly for various domains. For the external macroscopic field is 0. So, H is increased applying the current, and magnetic field of the domains tend to align with the applied field, and high permeability material like NiFe allows use the core construction to reduce this loss. So, typically core material with the initial unmagnetized magnetized domain typically. So, hysteresis loss depends on the area, I mean of typically of this your pH curve. So, you can call it, if you have a larger area you will have a larger loss, and you have a less area you have a less loss like I mean also. Now, coming to the second component of core losses, that is eddy current loss. This depends on the operating frequency and flux density, that is P equal to Ke into F P square into Bm square, where Ke is the coefficient of eddy current, F is the frequency in hertz, and Bm is the magnetic flux density in Weber per meter square. And we have a circulating current due to induced EMF in core. So, it results in excessive heating and power loss in core. It can be reduced by increasing the resistivity of core, and it can be achieved by eliminating the core and inserting thin layers of the insulating material between them, that increase the resistance for eddy current induced in the your ferromagnetic material. So, these are the eddy currents, as you can see induced in the eddy current in normal laminated core, that is for solid, that is for laminated, and that is the reason we laminate of course the core. So, now another loss is the winding loss. If it is a winding made with the copper, so we call it copper losses. So, copper loss in transformer is generally defined as the losses occur at the transformer winding, and depends on the current flowing through the winding. If R1 and R2 are the primary and secondary winding resistance, so we can say copper losses is equal to I1 square R plus I2 square R2, and non-uniform distribution of current in the conductor further increases the heating. There is another component of loss, we call it stray loss. The stray losses are additional eddy current losses in the structure path and within the winding, and leakage flux is responsible for these losses, and the leakage fluxes link the metallic structure part, tank, etc., and produce eddy current losses in them, and they take a place all around the transformer instead of definite place, hence the name stray, and the leakage flux is directly proportional to the load, hence this loss is called stray load loss. The stray losses are very low in air core transformer due to the absence of the metallic tank. Now, another loss is a dielectric loss, caused by insulating material and insulation such as transformer oil. It rarely occurs as compared to the core and copper losses. If the transformer oil is or insulation capacity gets deuterated, then dielectric losses increases. So, it can be reduced by two ways, by using oil testing or by maintaining the insulation capacity and quality of the oil. Now, coming to discuss the difference between the ideal and practical transformer. So, we can call it an ideal transformer is one that it has no winding resistance, it has no leakage flux, that is the same flux in both the windings, and no iron loss, the eddy current losses and hysteresis losses in the core. And we can call it like a perfect coupling between the primary and secondary, that is coefficient of coupling is like K m upon under root L1 L2, that is 1, and primary and secondary winding resistance are lossless, that R1 equal to R2 equal to 0, and primary and secondary winding have a large inductive reactance, that is L1 equal to N1 is proportional to N1 square, that is much greater than 1, and L2 equal to proportional to N2 square, that is much also greater than 1, and how it look like for ideal transformer here with the power quality of dot convention like. Now, we can say typically for this ideal transformer, the frequency domain analysis of this ideal transformer, that is V1 equal to j omega L1 I1 minus j omega m I2, that is V2 equal to minus j omega L2 I2 plus j omega m I1, and for ideal transformer m equal to under root L1 L2, and so V1 will be j omega under root L1 in bracket under root L1 I1 minus under root L2 I2. So, V2 is your j omega under root L2 in bracket under root L1 I1 minus L2 I2, and dividing both quantity. So, we get the V2 equal to under root L2 upon L1 V1, and that is V2 equal to your N2 upon N1 V1. That is the relation typically for the ideal lossless transformer, the input power output power. So, V2 I2 equal to V1 I1, that give you I2 equal to N1 upon N2 equal to into I1. So, then the mechanical analog this transformer is the typically with the lever. So, you have a typically here V1 which is and V2, that is you can call it the V2 here induced voltage N2 upon N1 into V1, and I2 equal to N1 upon N2 into I1, where here you can call it like a typically of this magnetic structure V2 velocity L2 upon L1 into V1, where length is L1, and here we have a force F1 with the velocity of V1, and here on the other side we have a V2 of lever, that is V2 with the force F2 with at the length of L2, and F2 equal to L1 upon L2 into F1. So, this is a mechanical analogy of the ideal transformer. However, a practical transformer differs from the ideal transformer in many respects. The practical transformer has a iron losses, it has a winding resistances, it has a magnetic leakage giving rise to leakage reactance. So, first is the iron loss is subjected to alternating flux. So, there occurs eddy current loss and hysteresis losses in it, and there are two losses together known as iron losses and core loss or core losses, or iron losses depends upon the supply frequency, magnetic flux density in the core and volume of the core material. And winding resistances, the winding consists of copper conductors. So, both primary and secondary will have certainly some definite winding resistances, and when current flow through the windings, there will be some power loss as well as loss in the voltage due to the I square drop. So, we have a leakage reactance in a practical transformer. The primary current will produce some flux which will not be linked to the secondary winding. So, similarly, secondary current will produce some flux that will not link to the primary winding, and the effect of these leakage fluxes will be the same as though through inductive reactance were connected in series with the each winding of the transformer, and primary and secondary winding are not lossless. So, there are resistive losses in the core as well as in windings. So, a practical coupling K m upon under root N2 typically 1 is not possible due to the flux leakage outside the core and winding typically. So, K is much less than 1, and another is the temperature rise due to resistive losses results in a formation of hot spot that can damage the winding insulation as well as core property, may change the core property, and short circuit forces due to leakage flux or magnetic field in between the windings carrying AC current, and the conductor in the winding exert force on each other leading to mechanical stress in the winding. So, the transformation from a certain RMS input voltage and current to value another different output voltage and current, keeping the AC signal frequency constant, that is salient features of the transformer. And transformation occurs by means of a common magnetic field shared between the two coils of primary and secondary, and no direct electrical connection between the input and output. Exception is the auto transformer, and static device with no moving parts, that is negligible maintenance, and highly efficient power transfer more than 98% from the input to output. Now, coming to the phasor diagram of the transformer on at no load. So, we can say here a transformer with its secondary circuit open as primary terminal connected to alternating voltage, and we have a small steady state current I phi called the exciting current flows through the primary and establishes alternating flux in the magnetic circuit, and this the flux induced an E1 induced EMF as E1 equal to d lambda 1 upon dt, that is N1 d phi 1 upon dt in the typically in the primary winding, and the applied voltage V 1 is equal to V 1 R 1 I phi plus E 1, and the instantaneous flux is phi equal to phi m sin omega t. So, induced voltage in the primary will be E 1 equal to E 1 N 1 d phi upon dt, that is omega N 1 phi m cos omega t, that is equal to in RMS value 4.44 f phi N 1 m, and E 2 will be N 2 d phi 2, that is omega N 2 upon phi m cos omega t, that is 4.44 f N 2 phi m. So, the induced EMF induced in the primary winding is displaced 90 degree from phi, and if it is used to show E 1 and E 2 in the phasor opposition with another, and V 2 appears in the position coordinate of the phasor diagram. That is typically phasor diagram. So, we have one V 1 E 1 and that is E 2, and this is the flux, and this we have a two component of this no load current. One is the magnetizing current, another is the your core loss component I O 1 and I M, and total no load current is the phasor sum of the two, that is your I M, and here phi is the angle at typically no load between voltage and current, and that phi is usually quite large, phi 0. So, the in no load current I 0 taken by the primary consists of two components, a reaction or magnetizing component I O M producing the flux, and therefore, the is phase with the flux, and active, that is typically this current, a active or power component I O 0 supplying the hysteresis and eddy current losses in the core, and we can say the no load current is I 0 equal to under root I O 1 plus I O M square, and the power factor at no load will be cos phi 0, that is I O 1 upon I 0, and the no load power factor is very poor. So, now coming to the typically some of the problems here, theoretical problem. So, what is a transformer? A transformer is a static piece of apparatus which transform electrical energy from a circuit to another circuit without changing the frequency, either stepping or stepping down the voltage. What is the theory of principle of operation of a transformer is based? The principle of operation of transformer is based upon the theory of mutual induction between the two circuit linked by a common magnetic flux. And then third question, what is the power factor of the transformer? The power factor of the transformer is very low and lagging at no load, but the power factor on load is nearly equal to the power factor of the load which is it carrying. What is the material used in the core of the transformer and why? Laminations of especially alloyed silicon steel, silicon content of 4 to 5% are used due to high electrical resistance, high permeability and non-aging characteristic and minimum iron loss. And how is the magnetic leakage reduced? The magnetic leakage is reduced by to a minimum by sectionalizing the interleaving the primary and secondary winding on the same limb. And what is the laminations, why the laminations insulated from each other? The laminations are insulated from each other by insulating varnish or thin paper to break the path of eddy currents and thus to reduce the eddy current loss. What is called grain oriented lamination? Grain oriented laminations are called such as cold rolled laminations, especially a need to orient the iron crystal into the grains into uniform direction in a direction of rolling, which produce loss. These laminations are punched and assembled in such a way that the grains of different laminations lie in the same direction as the magnetic field and need across it. What is the current flow through the transformer primary when secondary is open? When the secondary is open, there is no current flows in the secondary of the transformer, though primary takes a small current from the source called as no load current, which has a two component, a magnetizing component of current producing the magnetic flux and a working component supplying a real power loss for the iron losses and a small winding loss of primary. Why the frequency not change during the transformation of the electrical energy into transformer? As the same flux carries a definite frequency is responsible for the production of induced EMF in the both primary and secondary windings. So, there is no question of changing the frequency. Now, what is the you can call difference between a core and type and cell type of transformer? In core type transformer, primary and secondary are wound placed on each leg having one magnetic circuit, while the cell type of transformer both windings are placed on common central core having a two magnetic circuit. In the core type transformer, the iron loss is less copper lossage will be more as compared to the cell type of transformer. So, now I am coming to solve numerical problems. To calculate the phasor current I1 and I2 in the given circuit. So, we have a primary voltage RMS 12 volt at 0 degree, and we have a I1 current flowing into minus J4 capacitor reactant, and then the typically J5 ohm typically a reactance corresponding to the mutual coupling of transformer, and there is a mutual between J3 ohm and minus J6 ohm in secondary and 12 ohm load. So, we can have a KCL in first coil, that is minus 12 plus minus 4J plus 5J into I1, that is minus 3J I2 equal to 0. So, it give a relation J I1 minus 3 J I2 equal to 12, and coil 2 minus 3 J I1 plus 12 plus 6 J I2 equal to 0. So, that give I1 equal to 2 minus 4 J I2, and solving this we can get putting value to I2 we get 12 upon 4 minus J, that is 2.91 at the angle 14.04 ampere, and from this we can get I1 equal to 2 minus 4 J I2, that is I1 for 13.01 at the angle of 49.39 ampere. Now, coming to second numerical problem, determine the coupling coefficient for transformer. Here we have a resistance of 10 ohm, 5 millihenry, and mutual inductance of 2.5 Henry and 4 millihenry secondary, and capacitance of 1 by 16 farad. So, here coupling coefficient is K m upon under root L1 L2, that is K equal to 2.5 under root 5 into 4, that becomes 0.56. Now, numerical problem 3, ideal transformer has a transformation ratio of 0.125 and the primary current is 3 ampere when supplied from 240 volt, and calculate the secondary voltage and current. The transformer ratio is given N2 upon N1, that is V2 upon V1, I1 to I1 equal to 0.125. So, V2 will be V1 into 0 into 0.125, that is 30 volt, and I2 will be I1 upon 0.125, that is 24 ampere. So, coming to your fourth problem, ideal transformer connected to 240 volt means supply power to a 12 volt 150 watt lamp. Calculate the transformation ratio and the current drawn from the mains. So, secondary current is I2 equal to P upon V2, that is 150 by 12, that is 12.5 ampere, and transformation ratio is V2 upon V1, that is 12 upon 240, that is 0.05, and the current drawn from the supply will be I1 into I2 into N, that is 12.5 into 0.05, that is 0.625 ampere. So, coming to the fifth problem, for transformer circuit shown here, find the effective impedance and source current and the output voltage and the complex power supplied from. So, here we have a supply voltage 120 at the angle 0, we have a resistance of 4 ohm and capacitive reactance minus 6 ohm, and we have V1 V2 ideal transformer with 1:2 ratio, and we have a secondary load of 20 ohm voltage across V2. So, putting the all value, so we can say we first calculate that 20 ohm output resistance reflected to primary side. So, that becomes ZR primary. So, V1 upon I1 equal to V2 upon N I2, that is V2 upon N2 square I2, that is ZL upon N square, that is 20 upon 2 square, that is 5 ohm. So, effective impedance will be Zin equal to 4 minus 6J plus ZR. So, that becomes 9 minus 6J, that is 10.82 at the angle of minus 33.699 ohm, and I1 will be 120 upon Zin, that is 120 upon at the angle 0 divided by 10.82 at the angle minus 33.69 degree, that becomes 11.09 at the angle of 33.69 ampere. So, since both I1 I2 leave the dotted terminal, so we can say I2 equal to minus I1 upon N, that is minus 11.09 at the angle 33.96 by 2, that is minus 5.45 at the angle of 33.69 ampere. The output voltage V0 is 20 upon 20 I2, that is 1110.9 at the angle of minus 146.31 ampere, and complex power from source S equal to V S I1 square, that is 120 into 11.09 at the angle of 33.69 at conjugate. So, this becomes 1330.8 at the angle of 33.69 VA. So, coming to the numerical problem 6, a 5 kVA single phase transformer have a transformation ratio of 0.1 and is fed from 2.5 kilovolt supply. Neglecting the losses, determine the full load secondary current, the minimum load resistance, what can be connected across the secondary winding, and primary current at full load. So, secondary voltage is V2 equal to V1 into N, that is 2500 into 0.1, that is 250 volt, and at full load it is 5 kVA, V2 I2 equal to 5000, that is I2 give 5000 by 250, that is 20 ampere, and minimum load will be RL equal to V2 I2, that is 250 by 20, that is 12.5 ohm, and the primary current at full load will be I1 equal to I2 into N, that is 20 into 0.1, that is 2 ampere. Now, coming to solve problem 7, 100 kVA, 4000 by 200, 50 hertz single phase ideal transformer has 100 secondary turns. Determine the A primary and secondary current, B the number of primary turns, and the C maximum value of the flux developed in the core. So, solution is 100 kVA equal to V1 I1 equal to V2 I2. So, I1 will be your 100,000 by V1, that becomes equal to 100,000 divided by 4,000, that is 25 ampere, and I2 is 100,000 by V2, that is 100,000 divided by 200, that is 500 ampere, and N2 upon N1 is V2 upon V1, that is N1 V1 upon V2 equal to N2, that is 2000 turns. And EMF equation for ideal transformer, so E1 equal to 4.45 Phi1, N1 equal to phi m is 4000 divided by 450 into 2000, that is 9.01 into 10 power 3 Weber, and it becomes 9.01 milliweber. Coming to example 8, a single phase 50 hertz ideal transformer has 25 turns and 30 primary turns and 300 secondary turns. The cross sectional area of the core is 300 centimeter square. When the primary winding is connected to 250 volt supply, determine the maximum value of flux density in the core and B the voltage induced in the secondary winding. So, solution is the EMF equation for ideal transformer is E1 equal to 4.44 F phi 1 M1. So, we get phi m equal to 250 divided by 4.44 F 50 into 25, that is 0.045 Weber, and maximum flux density in core will be Bm upon phi m upon A, that is 0.05 divided by 300 into 10 power minus 4, that is 1.5 Tesla, and induced EMF in the second winding can be computed, that is N2 upon N1 equal to V2 upon V1, that is V2 equal to N2 upon N1 V1, that becomes 3000 volt. So, coming to solve problem 9, the maximum flux in the core of a 250 divided by 3000 volt 50 hertz single phase transformer is 1.25 Tesla Weber per meter square. If induced EMF per turn is 500, calculate the primary and second turns area of the core. So, E1 equal to N1 into EMF induced per turn. So, N1 will be 250 by 8, that is 32 turns, N2 is 3000 by 8, that is 375 turns, and E2 will be minus 0.444 F N2 Bm into A. So, from keeping this value of 3000 into 4.44 15 375 into 1.2, that A comes 0.03 millimeter square. So, coming to numerical problem 10, a 2200 by 200 transformer draws a no load primary current of 0.6 ampere and absorb 400 watt. Find the magnetizing and iron loss current. So, iron loss current is no load power input divided by primary voltage, that is 400 divided by 2200 equal to 0.182 ampere, and I0 square equal to I01 square Im square. So, from this Im is under root of 0.62 minus 0.182 under root of that. So, it comes your 0.572 ampere. So, similarly, there are some unsolved problems which you can solve in the similar line typically, and these are the references from which we develop this lecture material. Thank you very much.